Welcome to the first lecture of Symmetry, Structure, and Tensor Properties of Materials. And my name is Eugene Fitzgerald. I'm a professor here in the Materials Science and Engineering Department at MIT. And the MIT numbers for this class are 3.072, 3.60. The purpose of this class is to approach structure not from a solid state physics point of view, but from a geometric point of view. And then sticking with this geometric perspective to represent and introduce the representation of crystal properties in tensor notation. And so the class really is separated into three parts and almost equally in thirds. The first third being developing symmetry and structure for two-dimensional crystals. Before we head down that path, let's start with lecture 1, which is going to be discussing, just setting up some terminology, lattices, motifs, and operators. And we'll break this down into sub-components. So lecture 1 here we'll just introduce motifs and talk about a little bit about some simple operations. So the purpose of all this is to really get an intro into the field of crystallography, which, as I said, is connected through it's connected to properties of materials, and crystallography has different approaches. Like all things in academia, you can teach the properties of crystals in different ways. The properties are directly reflective of the crystal structure. If you've ever taken a solid-state physics class, for example, the way that electrons have their energies inside a solid directly reflects their electronic properties. And so the structure inside that crystal, how the atoms are arranged, their atomic number, how many valence they have, and everything else affects the properties. And it's true for everything, that the symmetry of the crystals actually affects their properties as well. And so that's why we're essentially doing this class. And you know, like any good field that reveals more about nature, there's experiment and there is theory. So experimental methods for revealing more about crystallography are X-ray crystallography. This is famous because the first way that people proved that crystals had periodicity. That's also one of the first ways in which people proved that X-rays and electrons themselves have wave nature and particle nature duality is through some of these characterization techniques as well. But here the purposes are we used an X-ray in order to reveal the periodicity of the crystal in different crystallographic directions. And so people that study crystallography, there's X-ray crystallographers. They spend all of their time, or most of their time, taking crystals and using X-rays to figure out what the structures are, which then would, of course, reveal something about their properties. There's optical crystallography. That is, if you were to use optical microscopes, polarization and things like that, you can also look at crystallography that way. And there's many different kinds of crystallographers and using different characterization techniques. For us, the relevant one is this geometrical crystallography, which is kind of an interesting way because geometry is theory pretty much. So you can think about this as theoretical crystallography. And what I find interesting about this, it's kind of really fascinating, is that geometry is in the abstract, and essentially when we use it to show or limit our experimental space or show how it's connected, really shows its full power. And the amazing thing about what we're going to do with the geometry in this class and symmetry is show that you can derive a lot of the background properties for these crystals because of their structure through just straight geometrical arguments. That's really fascinating because symmetry theory tells you that, well, if we set up some rules and we say that things have to fill space, well, it turns out that if you have to fill space and you have translational periodicity, it automatically means that there's a bunch of rules that appear, and already there's only so many possibilities you can have. And it's fascinating because that automatically means, of course, that you can identify how to start thinking about the properties of these materials, because it's not like you can have an infinite number of choices. There's actually certain rules that come in just from symmetry and geometry. So this is a bottom-up method, if you will. You could do a bottom-up method in physics where we put the atoms together and then we use Schrodinger's equation to understand how they could potentially interact and then how to minimize energy. That's one method. Here, it's kind of like a shortcut. You can say, hey, that's great. But the truth is, if we prefer to think about geometry instead of Schrodinger equation, we can get a large distance into sort of what these crystals have periodicity-wise, how they can organize themselves, and actually build complete crystal structures with these rules, even without thinking about Schrodinger equation once. So that's kind of the cool and different thing about this class. So let's start with some basic concepts. And one of the key things is that crystals have repeated periodic structure. So the key word in this sentence is periodic, which is that the structures have some sort of spacing, and it's repeated over and over again. The term motif is used to describe what is sort of hanging at each of these periodic points in space. So you can imagine that if I have a periodic structure, it could be the simplest one, a linear one, where I just have an array of dots. Let's draw that here. I just have a linear array of these dots. And then I can say, well, let's switch colors here to blue. And I have a star, very badly made star, that has the same, because it's periodic, has to have the same relationship at each point, and so on. There's another one here and another one here. Just put a point that, right? So the star is always the same place on each one of these green dots, right? So that's what we say hang. If I wanted to hang, I guess I should have drawn it downward. But basically, you have some feature that, here's the way we're thinking about the green dots are the periodic points, but I have square, rectangle, square, rectangle, square, star, rectangle, star, at each point, and it hangs on each one of those points, right? So these would be considered motifs, right? So if you want to have a fancy motif, you can see a nice purple one here, the letter L, and you'll see that a lot of times when we're going in and we want to show how objects move and we want to show different kinds of symmetries like reflection and rotation, it's going to be convenient to use a non-symmetric motif. Here it's non-symmetric motif, right? It's got an L shape, right? So you can determine handedness, which is a left and a right hand. And to see that, we can have a periodic structure where, for example, the handedness changes, or in this case, you can think of this as a rotation, right? And so if you can see here, this one here translates, but then it's also rotating at the same time, and it goes back and forth. So it's still periodic, but the motif actually is rotating. Or you could think about the following. You could think about, this is a little bit probably closer to a lot of the examples we're going to be using. You could think about that this actually is the periodic point here, and it's regularly spaced in the following way, and that we have two motifs hanging on each one. So here's one, and you can see it's like rotated and it's on the other side. And so we have this thing hanging on each dot. And so the motif here are the two purple objects. That's the motif that's hanging on the periodic structure here, which is, let's say, some lattice constant A, right, in a one-dimensional system. So again, now these we're going to find out later that actually the fact that this thing is rotated 180 degrees means that it's got kind of a symmetry, and we're going to use little symbols like a twofold axis, because this says that this is a twofold axis, because if I rotate 180 degrees, I get the other object about this point, right? But we'll talk about that in a minute. But we already can see that we can have multiple types of operations. This going from point to point to point is what we call translation. Here I'm describing the smaller translation, but if I look at this more complicated crystal, I could say, my translation's this one, and then the next translation's this one, the next translation's this one, because at each one of these points everything's repeated. So that's a translation operation. I show you another one here called the rotation operation, right? That operates about this point, right? So other examples, just to make sure you can think in multiple terms. I don't have to have a motif with two different kinds of shapes. In this case, shapes that are rotated 180 degrees about some point, right? I could have just a regular shape, and it's just repeated every so often. And in this particular case, it's the same example in a way, which I am unfortunately showing. I wanted to show something different, but again, this one has a 180 degree rotation about each one of these points, right? Another example is this one, where it flips back and forth. Now, what's interesting about these is that each one, as we look going forward, has a different, has actually different other elements in it. In fact, this blue one's kind of interesting, because if I were to draw a plane here, oops, sorry about that. If I were to draw a plane here, it actually isn't reflection, because if I were to reflect across this thing, I would end up with a shape that actually looks like this. So what I'm really doing is an operation where I reflect and I translate in order to get, this kind of shape. And we'll find out later that this is called the glide plane. It's a much more advanced operation. So there's all these different kinds of operations. The important one is the most simple one we're going to start off with, is a translation operation. It simply moves objects from one point to the other, and depending on what you choose to be the points in space, you can pick different kinds of translations, which we'll talk about. So these are basic concepts. Motif hang on the points that are described by the translation operation.